So we're combining what we know about our unit circle definition of our sine, cosine, and tangent. And then also that we're trying to memorize these values because I see coming in the near future, like right after Thanksgiving, a whole bunch of quizzes where you're going to have to demonstrate that you know how to do these things from memory. So these are things that we just in, like next year in calc, we'll just use all the time. You know, it's like the arithmetic of higher math. Question?
So I have a question about tangents. Is the tangent of an angle equal to the slope of the line that equal to the slope of the line that the angle makes?
Yeah, you can actually think of it that way. And that's the way we use it in calculus. It's not kind of yes and no. Yes, if you have a line, it is the tangent, and we'll get some problems like this eventually. It's the tangent is going to be the slope of that line where it crosses the x-axis. We will use next year in calculus the idea that if you take the graph of a function, we are really interested in finding the slope of the tangent line to the curve there. And that's a calculus question. You know, we talk about in pre-calculus that we could take another point on the curve and we could find the slope. We call that a secant line. We can find the slope of a line between two distinct points on a function curve. And then in calculus, we learn how to find the slope of that tangent line. In the case of this circle, yes, they are the same, but it's kind of a little different context because we're talking about a function curve rather than a unit circle. So, but then they're not too far off. But
so
they're not
if
exactly.
There's like an angle that's in the second or the fourth quadrant, then the tan of it is going to be negative?
Yes, exactly. That is true. So a tangent, yes, and that's an important way to think of it. So what Ronan is saying is because tangent is defined as a sine over a cosine, and we know the sine is the y-coordinate of the point on the unit circle, and the cosine is the x-coordinate. In quadrant 2, where you have a negative x value and a positive y value, the tangent of any angle in quadrant 2 is going to be negative. And likewise, the tangent of any angle in quadrant 4, because the x value, the cosine is going to be positive and the sine will be negative, tangent will be negative. In quadrants 1 and 3 are positive quadrants for tangent, because in quadrant 1, the x and y, the sine and cosine are both positive, and in quadrant 3, the x and y, the sine and cosine are both negative, and so a negative over a negative is also positive. Yes, so where the terminal side of the angle ends up, which quadrant it ends up in, completely determines the positive or negative sign. You have to be careful now when you say sine. So here I mean SIGN, the positive or negative sign of the sine, cosine, and tangent. Yes, that is, and that's exactly where we're headed with this. Now we want to also see that because a sine is the y-coordinate of these points on the circle, you can see that as we move along the circle here, and this is 0 degrees and 30 degrees and 45 degrees and 60 degrees and 90 degrees, that the y-coordinates of these points start small and get bigger. There's 5 values of sine and cosine that you need to know. And in order from small to big, they go 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1. And that's the way that I visualize it and the way I think of it. So when we talk about these in here, I'll try to give you this kind of visual hand gesture or arm gesture to get you to know the order of the angles, 0, 30, 45, 60, 90. Today we're going to add radians to that, whatever that is. And then know that sine goes from small to big. 0, 1/2, square root of 2, square root of 3 over 2, 1. And that's how you can remember them. So for me anyway, sine 30, what goes in my mind is I say, let's see, 30 degrees. We go 0, 30 degrees. It's like one click up. So then I know the order of those goes 0, 1/2. So the sine of 30 degrees is 1/2. And when you get to where you do this a bunch, that takes less than 5 seconds easily. And so we want to get that the sine of 30 degrees is a half. And you don't have to refer to a chart. You don't have to draw anything down. You can visualize it all in your head and do it quickly. Cosine 45, kind of one of two ways here. When you're starting out, you can kind of count them. Let's see, 0, 30, 45. Cosine starts big. So it goes 1, square root of 3 over 2, square root of 2 over 2. I think it doesn't take very long before you know that at 45 degrees, sine and cosine are the same. So that's kind of one of the first ones people memorize is 45 degrees, sine and cosine are both going to be square root of 2 over 2. And so that one comes pretty quick. Now, tangent of 60 is going to, when you do a tangent, it's really, you're doing two problems because you got to find the sine, you got to find the cosine, and then you got to simplify the fraction that comes out of that. So sine of 60, in my mind, I go, let's see, 0, 30, 45, 60. So that's going to be 4 clicks. So we're going to go 0, 1/2, square root of 2 over 2, square root of 3 over 2. So this is going to be square root of 3 over 2. Now cosine starts big, so it goes 1, square root of 3 over 2, square root of 2 over 2, 1/2. So it's going to be square root of 3 over 2 over a half. Then you can see that you can either just look and see the 2's cancel, or that you're going to multiply by the reciprocal. And so to divide by a half is to multiply by 2 over 1. The 2's are going to cancel, and so our tangent of 60 degrees is the square root of 3. That kind of makes sense, the reasoning that goes through there. So it all comes back to sine and cosine in quadrant 1. So if you know those 5 values for sine and for cosine, it's the same 5 values, and sine goes from small to big, and cosine goes from big to small. So there are one's in the order from least to greatest, and the other's the reverse order from greatest to least. So now when you get outside there, sine of 270, we need to know that, here's 90, 180, 270 puts us right on, it's called a quadrantal angle. So that's right on where the circle intersects the y-axis. So because it's a circle with radius 1, we know that the coordinates of that point are 0, -1, and we know the sine is the y-coordinate of that point. So that's how we know that the sine of 270 is -1. And that's how we're going to get 90, that's what we'll get 90, 180, 270, and any multiple of those. It's going to put us right on those quadrantal angles where we know what the coordinates are. And the cosine is the x value and the sine is the y value. Now, cosine -180, so negative means we're going to go in the clockwise direction. So -180 takes us right to, it's the same as positive 180. It's the same place. We know the coordinates of that point are -1, 0, and the cosine is the x value. So the cosine of -180 is also -1. Is that making sense? And now here we have the tangent of 90, which is again the sine over the cosine. And we know at 90 degrees, the coordinates are going to be 0, 1. And so it's the sine over the cosine. So that's going to be 1 over 0. But dividing by 0 is undefined. So crazily enough, the tangent of 90 degrees is undefined. Okay? Strange, but true. Questions on that? Any questions on anything else from any of those homeworks? It's been a while. Must be some good teaching going on there, I guess, huh? I take a week off and it's like you didn't even miss me. So what we're going to talk about today is 7.3 in our book, and this is known as Radian Measure. So this is a completely different way of understanding and defining how we deal with angles. So the issue where this comes from is that, we have all these functions that we talked about in all your math careers. As soon as you first learned about functions, you know, we have things like quadratics, x squared minus 3x plus 5. We've got our linears, y equals mx plus b. We've added exponentials. We talk about logarithms. All of these are functions of x. They're all functions. And what these all have in common is that you input a real number, and then the function does whatever it does to it, and you output a real number. So it's real numbers in, real numbers out. Sometimes that domain gets restricted so we don't get all real numbers. So we know, for example, a logarithm, you can only input real numbers that are greater than 0. And you'll output all real numbers. And for an exponential, it's the other way around. You input anything you want, all real numbers, and you output only the y values that are greater than 0. But still, there are real numbers in, real numbers out. Now, we are trying to start talking about things like y equals sine x, y equals cosine x, y equals tangent of x. We want to think of these as real valued functions. We want to input real numbers, output real numbers. The problem right now is the way we define our angles. Because we don't input a real number, we input an angle that's in degrees. So we have degrees in, and then when we get out for a sine or a cosine, remember, if we're thinking in terms of a unit circle, you know, you can plug in whatever angle in degrees you like, and what you get out is going to be a real number that's in between -1 and 1. So it's degrees in, real numbers out. But that's a problem because it doesn't play well with the others that we've talked about, because they're not consistent. They're not the same thing. All these other functions, which we want to at least join that list of real valued functions, we want to be able to input real numbers and output real numbers. The problem is right now we're inputting degrees. Now we may, in the context of a problem, choose to use this real valued function to model some kind of real life behavior. So we may talk about this being growth and saying, you know, the x is going to stand for time in years, and the y is going to stand for the population of humans in millions or whatever. But that's where we get to artificially put that in there. The function itself is unitless. Okay, we may impose that as we use those real valued functions to try to model some real life behavior. But as they stand, they're just real numbers in, real numbers out. They're unitless. And we want to do the same thing for our trig functions. And so to do that, we have to totally rethink how we do angles, which is tough because right now that's all you know about angles is these degrees. But when you think about it, that's really arbitrary. I mean, who came up with this idea that a circle is going to be 360 degrees? Why 360? That's really awkward. You know, and that a 90, when we say 90-degree angle, you know right away, you get a picture of what a right angle looks like, a 90-degree angle. Well, we're going to change that, and we're going to call these radians. So I'm going to do this two different ways. Well, I mean, they're related to each other, but I'm going to start with what we're going to call a wrapping function. So this is the idea to kind of suggest where we're going with this. So the wrapping function looks something like this. I'm going to start with our unit circle. So this is still going to, I'm just going to put a ordered pair here so that you know that I mean this is a circle with radius 1. Then imagine that you're going to take a real number line. So you're going to take this real number line here, and you're going to put 0 right here where the circle has the point 1, 0. And you're going to put the positives going up and the negatives going down. So on this number line are all of the real numbers. So every real number there is, pi is on there, e is on there, the square root of 7 is on there, -2 million is on there. So the positives go up, the negatives go down, and 0 is right here. Now you imagine that this real number line is flexible. So we're going to take the positive part and we're going to wrap it around this circle going counterclockwise. So we're going to take this positive and we're going to wrap it around there over and over and over and over and over and over again forever. So now what that means is that every positive real number has a place on this circle. Does that make sense? I'm going to take the negatives, and this is flexible, and I'm going to wrap it around there going clockwise, and around and around and around and around forever and ever. So now every place on this real number line has a place on the unit circle. So now what we can do is we can think of an angle as being maybe not so much the way we kind of think of it as like that space in between these two rays. We're going to now think of the angle as traveling along this circle, whatever length. So if we go here and we travel a length of 1, then that angle, so if this arc length on the unit circle is 1, I'm going to say that this angle theta is 1 radian. Yes?
Does pi somehow relate to this?
It does indeed. It is very kind of integral to this. So yes, some of the special angles we've been talking about, like 30 degrees, 45 degrees, 60 degrees, 90 degrees, and so on, are related to pi. So first let me make sure we understand. So this is a length of, so this is an angle of 1 radian. Now, I have written the word radian on there, but what happens is this is unitless. This is just like on the number line. So if we talk about now, what we're going to talk about shortly is, if we say sine of 30 and we do not put the degree bubble on there, then that is understood to be 30 radians. So now it becomes critical that if you're talking about something in degrees, which we're going to kind of bounce back and forth in here. The good news, bad news is next year in AP Calc, we will never talk about degrees. All of AP Calculus is in radians, and higher math is done in radians for the same reasons we talked about, because we want to mix these trig functions in with all of our other functions, and they have to be consistent to be interchangeable. And so if you don't write the degree bubble, that's understood then to be in radians. Now, let's get to Ronan's question, which is a good one. What's this connection to pi? Well, what we know is that the circumference of a circle is 2 pi r. So in our case here, we have chosen this circle to be a radius of 1, which means that the circumference is 2 pi. That means that this trip all the way around the circle, one trip around the circle, is 2 pi radians. That is equivalent to 360 degrees. Those are equal to each other. So that means if I divide by 2, then pi is the same as 180 degrees. So what that means is all of these nice angles. Now, it's still, this angle of 1, this angle of radian 1 is not a multiple of pi, right? But the nice angles that we talk about, like pi and 2 pi, so a 90-degree angle would be the same thing as what? It would be 1/2 pi, which we will write as pi over 2. Okay? And so this angle in radians is going to be pi over 2. This angle in radians is going to be pi. This angle in radians is going to be 3 pi over 2. It's 3/2 pi or 1.5 pi, but we'll call it 3 pi over 2. And this angle is going to be 0, but it's also 2 pi. And so now these angles, like we've seen with degrees, too, are not unique, right? Just like we said that an angle of, say, 30 degrees is we said coterminal with 360 plus 30 is 390, that these are coterminal angles. They end up in the same place. And because they end up in the same place, the sine and cosine and tangent of a 30-degree angle will be the same as the sine and cosine and tangent of a 390-degree angle. Okay, so we can think, what we want to do is to think in radians. So what we want to learn to do is take this unit circle. Now we are real familiar with, in our own mind, what a 30-degree angle is, a 45-degree angle, and so on. So what we're going to do is rethink this in terms of radians, so that, and I like to think of it as in terms of 1 whole pi. So this semicircle, this 180-degree angle, is the same as 1 pi in radians. So now if we divide this 1 whole pi into different fractions, we get a feel for what these common angles are. These angles that we like to, for example, know and memorize the sine and cosine and tangent of are in terms of pi. So this will be pi over 2. If we look at what we would have called a 45-degree angle in degrees, we can see that it is 1/4 of a pi. And so this angle will be pi over 4, or 1/4. This is 2/4, which reduces to pi over 2. This one in quadrant 2 will be 3/4, which is 3 pi over 4. And then our whole pi is like 4/4. So you can see 1/4, 2/4, 3/4, 4/4. That make sense? You can see that if we divide this into thirds, right, where this is the 1 whole pi, then we're going to have 1/3 pi is going to be right here, 2/3 pi will be right here, and 3/3 pi is going to be 1 whole pi there. And we've split that 1 whole pi into thirds. And that's the way we want to think of it. Instead of having to always convert back and forth from degrees to radians, sometimes we'll have to do that. We'll talk about that in a moment. But to visualize it and think of it in terms of thirds of a pi is going to be better. If we divide this into 6, then 1/6 of 180 degrees is 30 degrees. And so we're going to get here is our 30-degree angle is going to be pi over 6. The 2/6 reduces to pi over 3, to 1/3. That's that yellow one, that's our pi over 3. So there's 1/6, 2/6, 3/6 is pi over 2, 4/6 is 2/3. Over here in quadrant 2, we're going to get 5 pi over 6, or 5/6 pi. We can continue over here. Notice a straight line here. This is going to be 1 and 1/6 pi, 1 whole pi, plus a 6 pi, 1 and 1/6, which is 7/6 pi. And if we extend this down here, this is 8/6, which is like 1 and 1/3. 1 and 2/6 is 1 and 1/3, and 1 and 1/3 is 4/3 pi. 9/6, down here, right on the y-axis, 9/6 is 1 and 1/2 pi. We talked about that a little bit before. There's our 3 pi over 2. Extending this 2/3 pi angle straight down, that's supposed to be a straight line. So now we have 1 and 4/6. 1 and 4/6 is 1 and 2/3. 1 and 2/3 is 5/3 pi, or 5 pi over 3. And if we extend the 3 pi over 4 down here to quadrant 4, this is now 1 and 3/4, or 7 pi over 4. And extending the 5 pi over 6 down into quadrant 4, I like to think of this as being 2 pi, which is 12/6, 2 pi, which is 12/6, back up 1/6 pi. So 12/6 minus 1/6 is 11 pi over 6, or it's also 1 and 5/6 pi. 1 and 5/6 is also that 11 pi over 6. And then we're back to 2 pi here, which is the same as 0. So this is going to be a better way to kind of visualize that. And I might have enough here. I have some of these. That one's particularly dusty. This is drawn out there to help you see it. And we're going to talk in a few minutes here about the sine and cosine of those. And you're free to write on that if you like.
Wait, so in radians, can 2 pi always equal 0? Like, are they such?
Yes, they are coterminal angles. So they will act as equivalents. So 2 pi, 4 pi, 6 pi, 8 pi, and so on, all act exactly the same as 0. They're in the same place. They're right on that positive x-axis. Okay, now let me back up a little bit. We have defined this in terms of the unit circle because I think it's easier to conceptualize that way, but it is not limited to or restricted to a circle with radius 1. So if and I'm just going to challenge myself here, I'm going to try to draw another circle here centered at the origin with a different radius. I don't recommend doing this. So there is our circle there now. And so we're going to say that its radius is r. So it could be bigger than 1, it could be smaller than 1. Now, this angle that we saw here, that is, we said is 1 radian, right? Because on a unit circle, you just travel along that arc length, you travel along that circle a length of 1, and where you end up, that defines where that angle of 1 radian is. Well, that we said because the circumference is 2 pi r, which is just 2 pi, that's why that length of 1 defines that angle of 1 radian. Well, if we have a circumference and the radius is not 1, it could be something else, then, so let me back up. So this means that that full circle is 2 pi radians. So coming all the way around the circle takes a length of 2 pi. Well, now what we do for an angle, for a circle that has a radius other than 1, is this same angle will be a length of 1 radius. So if we travel r along there, there are 2 pi of those arc lengths all the way around the circle. And so this circle of radius r, if we travel a length of 1 radius, it gives us an angle of 1 radian. It's the same angle that we got on the unit circle by traveling a length of 1. So it doesn't have to be tied to a unit circle, although I think it's just easier to conceptualize when you make it a unit circle, because then it is exactly the arc length. Yes.
Does that angle get a name or something, or is it just?
Its name is 1 radian. So we say that an angle theta is going to be, this is written as the arc length divided by the radius. And so then you can see that an angle, so that's our definition of an angle in radians. So I'm going to write theta sub r. And I don't know why S is used for arc length, but everybody does. It doesn't seem intuitive to me. So if you measure an arc length divided by the radius, that is an angle of 1 radian. I hate to erase any of this, but that's going to be it. That's our angle in radians. So when the arc length is 1 radius, then our angle is by definition 1 radian. And so that's just an angle of 1.
Okay.
So it takes a little while to kind of wrap your head around it. So let's imagine, and just to make things easier, let's just imagine that this is a unit circle. So can we mark on here an angle that is 1 radian? Can we mark one that is 2 radian? Can we mark one that is, say, a -3 radians? So notice there's no degree bubble on there. And so that's how you know without the degree bubble, we must be talking about radians. Now, what we want to do, to get a kind of an intuitive feel, because we have a good understanding of degrees. Oh, I'm never going to have enough time here. So we have a good idea of degrees. Since there are 2 pi radians in a full circle, and pi radians is a semicircle, then our pi is equal to 180 degrees. And so pi is like about 3.14. So there's a little more than 3 radians in a semicircle, a little more than 6 radians in a full circle. So an angle of 1 radian is real roughly about 1/6 of a circle. And so an angle of 1 radian is really roughly 60 degrees. It's actually more like around 57 degrees. Not exactly, but approximately. Because remember, you're dividing by pi, so it's not going to be exact. But that just gives you kind of a ballpark figure. So then you know then an angle of 1 radian, because you know what a 60-degree angle looks like. So an angle of 1 radian is going to be somewhere there in quadrant 1. An angle of 2 radians is going to be roughly 120 degrees. It's going to be in quadrant 2 here. So here is an angle that is 2 radians. And an angle of -3 radians, we know that that is going to be, negative is going to come around here. And we know if we went all the way to a semicircle, that'd be pi, which is roughly 3.14. So 3 radians is going to fall a little bit short of a full semicircle. So it's going to be somewhere in here. So that is going to be our angle of -3 radians. Yes.
Is the 60-degree angle like always close to 1 then?
Yes. Always. Yep. Okay. Now our conversion is this. So if you are a science person, you know about unit factors. So if you divide by 180, then you know that pi divided by 180 degrees is equal to 1. If you divide by pi the other way, then 180 degrees over pi. And this is how we're going to convert from degrees to radians, radians to degrees. You may, if you get stuck, you may need to check on that. There's a video in the supplemental videos, and you can kind of go to the end and see some of these kind of problems worked out, because we didn't get to those today. All right.